So good morning, everyone. I'm Nezihe. For those of you who weren't here yesterday, I tried to give a brief summary about cosmology, and I divided those two lectures into two, more of a simplistic version, and today will be about more of a realistic version of cosmology. So yesterday we talked about GR, basic concepts on physical concepts, mathematical concepts relevant for us. And I talked about simple tricks to solve Einstein equations, which are usually very hard to solve for realistic scenarios. And I said that you can either go to a weak limit to have solutions like gravitational waves, or you can impose some symmetry conditions on your system so that solutions are easier to be solved. And we applied this trick to cosmology by applying some assumptions on the universe, and that gave us some symmetry conditions. We said that we assume that the universe is homogeneous and isotropic, and that gave us a very simple solution yesterday. And then I tried to give a brief summary of the standard cosmology we use today. And I talked about the relevant observations. Those were the supernova observations that we measured the luminosities of the supernova that are really good standard candles versus the redshifts. And that's how we interpreted that the universe is accelerating. Then I talked about the Swiss knife, the cosmic microwave background radiation, that we can get nearly all of the cosmological parameters we need today for our standard model. And then I talked a little bit about the light element abundances, Big Bang nucleosynthesis, and I said that this process sets the cosmological parameters in a very convenient manner. So today we're going to have a reality check, and I'm going to talk about the problems of the lambda CDM, and then I'll give a brief review about the alternatives, like modified gravity, how to modify GR or the cosmology in general. And I'll talk about the real cosmos, how the universe really looks like. And this will give a motivation about a viable alternative to the standard cosmology, which are inhomogeneous cosmologies. I'll give a brief summary of the concepts and the mathematical constructions about that. So, okay, lecture 2. So here's our standard model. We talked about it a bit yesterday. We said that the 95% of the energy budget we have today is unknown. So about 27% is in the form of dark matter, which are not detected until today. And about 69% is in the form of dark energy. And we're only left with 5% for the ordinary baryonic matter that we know of. So, and the actual physical mechanisms behind this dark sector is unknown. We don't know. We know how to interpret the data, we know how to modify our standard model, but we don't have physical mechanisms to drive these unknown phenomena. So now I'll start with some problems of the standard model, and the first one will be about dark energy, which we also call the cosmological constant in Einstein field equations. So as you remember, we modified the Einstein field equations by introducing a scalar field to mimic this accelerated expansion of the universe. And the interpretation of this lambda initially came from the quantum theory, because both the energy density, both the physical effect of this cosmological constant and the vacuum energy is repulsive in nature. And the high value of vacuum energy is already expected in the early universe. Particle physicists, quantum field theory people already knew about that. And there were processes to make it exactly to zero, annihilation of the virtual particles, etc. And they were expecting this term to be exactly zero. So when you go and calculate the energy density of vacuum at the Planck era, it's about 10 to the 110 ergs per centimeter cubed. But from the observations we have today, we expect the energy density of the cosmological constant to be 10 to the minus 10, or order of 10 to the minus 10. So this is off by 10 to the 120. That's why it was said that in the literature it's the worst theoretical prediction in the history of science. So this is the dark energy problem, cosmological constant problem we have. Then another problem comes out. If this is true, if dark energy is predicted by the vacuum energy of the quantum fluctuations, then there has to be an extreme fine-tuning to bring this value to that value, which is already very small. So this is the fine-tuning problem in cosmology. And again, we don't know if there's any physical process which would bring down this large value to the small one. So another problem which is related to, again, dark energy problem is the Hubble's parameter. So remember yesterday when I was talking about the magnitude of the Hubble's parameter, I was saying about 70%. I couldn't give you an exact number because of this. So those are the experiments done, cosmological experiments. Horizontal line is gives you the years that they're done, and the vertical line gives you the axis gives you the magnitude of the Hubble's parameter in kilometers per second per megaparsecs. So the green experiment, the red experiments are the ones related to early universe. When you interpret the magnitude of Hubble's parameter from the cosmic microwave background radiation data, for example, you get smaller results. But if you go and do the experiments via the supernova experiments, for example, which are closer, when you look at the look-back time, you get larger values. And you see that it has nothing to do with the error bars, because we're in the precision era experiments and the error bars are really well set. So this shows that there is a discrepancy in the Hubble's parameter depending on how far you look or the method you look, like whether you're using standard candles or standard rulers method. And this discrepancy still cannot be solved. So this is the second problem of the standard model. Third problem has to do with the inflation phenomena, and it brings the old flatness and horizon problem. So the standard model, as I tried to explain you yesterday, tells us that the spatial sections of the universe is almost flat, not exactly flat, almost flat, and the energy density of the universe is almost close to the critical density. So this means that, and that is the value we have today. This means that if you go to the early universe and try to understand the condition back then to get this value today, you see that at the Planck era, when the universe was 10 to the minus 43 seconds old, universe should almost exactly be flat, like exact flatness. So you can only depart from unity in part in 10 to the 62. That means your initial conditions are extremely fine-tuned, and that was the flatness problem in cosmology. People didn't know how to explain it. And then when you look at the cosmic microwave background radiation, you know, I said that you can go and look at any direction and sorry, you expect an isotropic distribution of temperature, right? But when you look at in one direction and then the other, which are very far away from each other, and then you go and calculate, and then you realize that those regions were never really causally connected back in the future. And that doesn't make sense because the data shows you that the distribution is almost the same over the sky. So this is called the horizon problem. Regions which weren't in the particle horizon has the same properties. So it was during 80s, Ellen Guth and Andre Linde came up with a solution, which is inflation. So They said that at this very early era of when the times were between 10 to the minus 36 and 32, the universe went through an exponential expansion, which was huge in a very short amount of time. So that means even if you had some initial fluctuations in your gravitational potential, this huge accelerated expansion, this exponential expansion, stretches out the inhomogeneities. Thus, we now have a flat universe, and separates the region once. So there were those regions that we observe on different parts of the sky were really once causally connected, but because of the inflation, they got stretched apart very far away locations. So the theoretical construction of the inflation is obtained by assuming a scalar field. So you write your stress energy tensor, remember, at the right-hand side of the Einstein equations, via the scalar field. An equation of state looks like that. So if your potential has such a property, which means it has a slow roll, initially it has a plateau, and then it slowly rolls down to a lower value, then this omega equation of state roughly becomes -1. And when you go and plug this into the Einstein equation with the simple FLRW solution on the left-hand side, you get an exponential expansion for your scale factor. So the universe expands in this very short amount of time. So the problem of inflation is that, again, there's no physical mechanism behind it. We don't know how it worked, what triggered this. We don't know whether it exists and whether there's any physical mechanism to have the specific profile we need to get this exponential expansion. So Planck team, which is the same team that make this precision experiments of the cosmic microwave background, ruled out many of the inflation scenarios because there were many models to model this phenomena, and Planck team ruled out many of them. And nowadays, even the creators of inflation start to having doubts. And those are basically because the shape of the potential curve that I showed you is controlled by a numerical parameter. And now we know that, thanks to the experiments, it should live in a very narrow range. It should be this. So this is another fine-tuning problem we have in order to have the current temperature variations on the sky. And for example, Penrose, even at the early times, he wanted to check whether this makes sense for the thermodynamic principles. So he found out that a flat universe without inflation is 10 to the 100 times more probable, more likely to have a flat universe than not having the inflation at all. And by nature, inflation is actually eternal, and you need to have a mechanism to stop it. So if the inflation is eternal, and initially you have some quantum fluctuations, that becomes problematic for observables, right? Because imagine you have random fluctuations which evolve eternally. That means you have all the probabilities that you can have within the universe. So Steinhardt, which is one of the founders of the inflation, is now writing articles against inflation. So this is one of the quotes that I'm gonna show you here in one of his latest articles. So he says, what does it mean to say that inflation makes certain predictions if anything that can happen will happen an infinite number of times? That doesn't make sense. So, and if the theory doesn't make testable predictions, how can cosmologists claim that the theory agrees with observations as they routinely do? So, so people in the community started having doubts, and that includes even the creators of inflation. So, the next problem, dark matter. I think you are more interested in this problem than anything. And I would say that this is probably the hardest one to solve because it exists in many of the scales in the universe. For example, you observe in galaxies, in the galaxy cluster scales, and in the early universe. So wherever you look, it looks like there's some missing mass problem. So in the galaxy scale, we say that the rotation curves are the basic examples to show that there's a missing mass. So on the vertical axis, you have the radial velocities of the stars in the galaxy, and on the horizontal axis, you have the radius. So this is the predicted curve that we predict with the Kepler's law. Basically, you expect a constant disk, you need an increase, and then drop with the square of the radius. And the one on the top is the observed one. There's an increase and there's a flattish profile that shows that there must be some extra matter that causes such a and we cannot observe because dark matter does not interact with the photons. And that's how the early, even in 30s, people started predicting of this missing mass problem in the galaxy profiles. So, and yeah, that is my note. Remember that this prediction is Newtonian, like Kepler's, by using Kepler's laws, and there are no exact general relativistic models to model galaxy rotation curves. Just keep that in mind. And in the galaxy cluster scale, you can determine the mass via either radial velocity scatter of galaxies, and this gives you the baryonic matter. And you can have the X-ray spectrum of the hot gas, and you also do some gravitational lensing experiments. And in the galaxy cluster scale, the famous example that we give is the bullet cluster. And that is mostly obtained by the gravitational lensing data. Okay, so let's say you're on Earth and you want to observe a distant galaxy. If there's an intervening galaxy cluster or some object, the light of this distant galaxy that you want to observe is bendant, and you see multiple images of this distant galaxy. So by looking at the image that you have of this distant galaxy, you can have an idea about this intervening galaxy cluster's mass, right? This is how you get the gravitational lensing data. So on the right, you have a bullet cluster. That is a cluster that gives the collision of two clusters, basically. So there are hot gas, stars, and dark matter. We assume that there's dark matter. Well, I'm going to explain it now, why we assume so. And they behave differently during this collision. So stars are not much affected, and the hot gas slows down much more the stars because that is where most of the mass is. And then you expect your gravitational lensing data to follow the hot gas, because you say that, okay, most mass is in the hot gas form, the gravitational lensing data should follow the hot gas. But then when you look at the lensing profile, you see that the data favors two separated regions that we cannot observe via the X-rays or any kind of electromagnetic spectrum. So this is one of the best examples of the fact that there must be some additional matter in the galaxy cluster scale, which the gravitational lensing data favors. So, and then we have the early universe, proof for dark matter in the early universe, and that comes with the baryonic oscillations, baryonic acoustic oscillations data. So remember yesterday I talked about this early universe. There was a very energetic plasma. Yesterday I talked about the baryons and the photons. Let's say we now put some dark matter into the problem. Now, there are two forces fighting in the early plasma, gravity and the photon pressure. So, gravity, which is the gravity of the baryons and dark matter, will try to pull everything down, right? And the photon pressure will fight back to this gravity's pull. So they will start oscillating in a manner. But dark matter is not interacting with photons. That means while this fight is going on, dark matter will clump in the middle, but baryons will follow this fluctuation and they will form in a spherical form. They will take a spherical shape, leaving the dark matter in the middle. If there is dark matter, that would be what you would expect. So, and we talked about this decoupling era, where when all these fights were going on, the universe was also expanding and the temperature was dropping down. This gave the photons and the electrons to couple, right? And the photons started free streaming. That is what the cosmic microwave background radiation is, the thing that we talked yesterday. So by looking at this data of the relic radiation, you can see that this spherical distribution that I talked about can be viewed in the galaxy correlation functions, because it is these initial quantum fluctuations that give seeds to the structure today. So by looking at the structure today, the galaxy correlation functions, like say you have a galaxy and then you try to find out the most probable distribution of the closest galaxy, you see that this is actually what we observe as you would expect from an early universe, with a dark matter clumping in the middle and the baryonic matter in a spherical distribution. So this galaxy correlation function peaks at 150 megaparsecs. And this is another very important sign of the fact that we need some dark matter in the universe, in the early universe, to see the structures as the way they are today. But this dark matter is, of course, problematic, as you might have heard. There are small-scale crises. There's this famous cusp core problem. So the predictions, our theoretical prediction says that there must be a cuspy core in the center and then low outer densities. But the observations see constant density core and flat outer profile. So, and then there's the satellite problem. You expect near your, let's say even near Milky Way, you predict more satellite galaxies around your own galaxy than the observed one. For example, when you do some simulations, you expect about 500 satellite galaxies for Milky Way, and we observed just 11 of them, as far as I know. So, and the predicted angular momentum is much smaller than the observed one. And the prediction says the bars rotating in the dense halos should slow down due to the dynamic friction, but that's not what we observe. Bars rotate quite fast, actually. And there are galaxies without any dark matter at all, and that was pretty puzzling for some people. And of course, most importantly, despite all the effort of detecting dark matter, spending millions and millions of dollars, putting these experiments underground, in salt, in ices, and people tried to detect it directly or indirectly, and we still couldn't detect dark matter. Okay, the fourth problem. The fourth problem is about CMB anomalies. So yesterday I said that we observe an almost isotropic distribution, but there's an expected anisotropy in the temperature, and this is coming from the early universe quantum fluctuations. We can predict it, we can match the data to our model. But there are some anomalies that we didn't expect, and this is a puzzling problem for some of the researchers. So there are some properties for the CMB we expect from the early fluctuations. So it should be statistically isotropic, it should be Gaussian with random fluctuations, it should be almost scale invariant, And we expect phase coherence of fluctuations because we observe different, so we observe CMB in different frequencies, and we expect a phase coherence. We expect the dominance of the adiabatic mode, which means you expect your gravitational potential flattening in time, and some more like a cosine wave should be the mode that dominates. And there are no rotational modes at large scales for your polarization data. Those are the predictions we have for the CMB. And one of the problems are there exists a cold spot on the southern hemisphere. So there's a specific spot which is colder than we expect, which destroys the scale invariance or isotropy, which we do not expect. Some people assume that maybe there's a giant void behind it, that made the data look more colder, but that didn't turn out to be the case. So this is still puzzling. And at the scales larger than 60 degrees, you see a drop in the correlation of the temperature. That can have a primordial origin or a local origin. People don't know. And there's an asymmetry between the northern and southern sky, and we still couldn't put a finger on what it really is about. And there's this axis of evolve, which is pretty spooky because it's the alignment of the quadrupole and the octopole moments. So it looks like the solar system is in such a movement, such a kinematical movement, or in such a position that for every hot spot there's a corresponding cold spot. Like, some people say that there's something wrong with the statistic we use, or maybe something wrong with the instrumentation, but this problem still haven't been solved. Okay, the last problem I'm going to talk about is the lithium abundance. So we talked about the light elements abundances yesterday. We said that in the early universe we have some hydrogen, helium, some deuterium, helium-3, and a little bit of lithium. So here's our expectation from the Big Bang nucleosynthesis. And according to the Big Bang nucleosynthesis, the ratio between lithium-7 to hydrogen should be something around 4.16 to 5.34 times 10 to the minus 10. And when you go and look at the data for metal-poor halo stars, you see that what you observe is 3 times less than what you predict. And there's also a problem in the isotope ratios of the lithium-6 to lithium-7. You expect it to be at the order of -5 for the predictions, and what you observe is something around 10 to the minus 2. So this is another story in a different level, which is still waiting to be solved. So those were the problems of the standard model. And okay, this is about the fact that the second problem is less robust. Yeah. So those were the problems of the standard model. Now I'll try to give a brief summary of what the alternatives are for the standard model we use today, or the gravitational model we use today. So when this dark energy problem first came out, the string theory and quantum gravity people's research was really at its peak. So when this problem came out, they all rushed to solve the dark energy problem by modifying gravity, I can say. So this is the action that generates Einstein's field equations. So in the so this is the four-dimensional volume element. The first two terms give you that. Square root g gives you the determinant of the metric, four-dimensional metric. R is the Ricci scalar that gives you idea about the curvature of space-time. And you can put lambda, of course, to your model. And the LM is the metric Lagrangian. So you extremize your action with respect to the metric, and then you reach your Einstein field equations, right? So the idea is to modify this action in order to have some modified field equations. The first thing you can do is to add some extra fields. For example, it gives you a scalar tensor theory. You couple some scalar field to your geometry, not necessarily to your model, and you end up with a modified action that gives you modified field equations. And you can do that with some vector field, introducing vector fields in your Lagrangian density. And again, you're not coupling it with your matter. And this adding extra fields goes up to adding another metric to your model, and that are biometric theories. Let's say this you have a tilde metric which is static. Then you can define a dynamic metric by defining by adding another perturbation on it, or which doesn't necessarily be small. Then you end up with biometric theories and a modified gravitational action that would eventually mimic the effect you want to get in the end. The other modified theory is the modified Newtonian dynamics, which are relevant for dark matter problems. So what you do is the modified inverse square law of Newton. There is a specific acceleration turnover that in the values higher than the specific value, you expect the Newton's law, and for the lower ones, you modify your gravity. And actually, Mond fits the galaxy rotation curves pretty well. I mean, people didn't expect it to be so well, and yeah.
What about these galaxies that were observed without that part?
Yes, right? And what about the galaxy cluster scale? Because most of the time they don't fit they cannot explain the cluster scale or the early universe data. Because, yeah. But then it might give you some signs about what we should be expecting in the galaxy scale, maybe. Still, because it's fitting data pretty well. So, and yesterday when we talked about the curvature terms, the Riemann and Ricci curvature tensors, I said that they include this up to second order derivatives of the metric. So that is important. What you can do to modify your gravity, your action, is that you can introduce higher order derivatives to your action, right? And the most famous one is the FR gravity. That was something for the last decade, I would say. People were introducing new functions to the actions by just replacing this Ricci term by a function of Ricci itself. So you can go further and even parameterize this FR gravity theories, and each would be just a parameter in the FR gravity. So if you replace your Ricci scalar by a parameterized function including the invariance, curvature invariance, you put the FLRW metric on the left-hand side, you get an evolution equation for the scale factor, and those are all constants basically. And that's why for different cosmological eras, by just manipulating your parameters, you can really fit your data and predict whatever we observe today. But then again, there's no physical mechanism behind this. I would say it's much of a mathematical trick. And there are others, like you can add additional terms of squares of the Ricci or other invariants of the curvature invariance. You can even go and follow a teleparallel approach that gives you the same kind of observations. So in GR, we assume that torsion doesn't exist. The Riemann tensor, the curvature tensor, has certain properties, and we get this by turning off torsion. But there's another method to have similar physical results you turn on torsion and you get rid of the symmetries of the Riemann tensor. So this is a teleparallel approach, and you can even modify this teleparallel approach to modify gravity. And then there are higher order theories. So gravity is defined on can be defined on a 3+1 manifold. So you have three-dimensional spatial slices which evolve in time. And if you want to go to higher dimensions, like in the Kaluza-Klein gravity, you can apply GR to 4+1 dimensions, and this one extra dimension being very small. Then you assume a Bianchi type metric with Einstein field equations. That is, you have a scale factor for the standard physical universe you have. And then remember, there's this small extra dimension. You can have another Hubble's parameter, tilde 1, for this extra very small dimension. Then you go and write your Einstein equations with the scale factor. So this is just one of them, with the scale factor of the physical universe, Hubble parameter for the physical universe, and this extra small dimension. So when you collapse the small subspace, take the scale factor, go to 0, and your Hubble's parameter for this extra dimension becomes very small, that can create the effect of accelerated expansion in your physical space. So this was another method to have this apparent accelerated expansion effect, the way to modify gravity. And there's the brane world paradigm. This time your extra dimension doesn't even have to be small, and it can even be infinite. And it is the brane tension that compensates this bulk effect of the cosmological constant. So the tension, you have a universe embedded in a higher dimension, and it's the tension of the brane that creates as if there's an accelerated expansion. So this is kind of a summary of how to modify gravity in a very short time. Now I'm going to talk about a viable approach to as an alternative to the standard model, and that is inhomogeneous cosmology. So why is this a viable approach? When you go and look at the late-time universe, it is actually highly homogeneous. You know, initially we said that universe is very homogeneous and isotropic. That is true for the early universe. But the current data shows that universe is far from being homogeneous. So this is the actual data from Sloan Digital Sky Survey. So you can see this black regions. Those are the data that are contaminated by our galaxy, because there is some, contamination due to our own Milky Way. So we get rid of this data. And the redshift goes to 0.14. So as you see there, and here, all the dots refers to a galaxy, which has like 100 million stars in it. So you see structures and big structures that will give you that there's in fact a statistical homogeneity if it exists at all, and that is on the scales larger than 100 megaparsecs. And okay, here is the Millennium simulation. So you can see that in your simulation as well. This is like around 125 megaparsecs over little h. Here h is the your Hubble's parameter divided by 100. So even in the simulations, you can see that the late-time universe is not homogeneous at all. We have filaments and voids dominate in general. And there are actually structures larger than the statistical homogeneity that I was talking about. Is there a question?
Yep.
Yeah.
The other picture you had of the Sloan,
Uh-huh.
so you have a redshift scale. So That's a radial scale here?
Yes, yes. So it's in the look-back time, actually. When I said redshift 0.14, that is like looking back in time on your past light cone. And so it's like 1.8 billion years, I would say. Yeah, roughly. So yeah. But the relation between redshift and look-back time actually depends on the cosmological model you have as well. So that is tricky. So yeah, I was saying that there are objects larger than the statistical homogeneity scale, which is roughly 100 megaparsecs, as I said. For example, this is from the 2-degree field galaxy redshift survey, and you see like Sloan Great Wall is around 100/h megaparsecs, and then we have Boss Great Wall, which have 4 small structures, not small really, 186, 173, 91, and 64/h megaparsecs. And there's this giant void, they call it, which is in the size of 180/h megaparsecs. And okay, to give you just an intuition, Sloan Great Wall is like the 1/60th of our observable universe, and this is just one structure, and it is not the greatest structure in the universe. So I don't know whether it really makes sense to really talk about some even statistical homogeneity of 100 megaparsecs at all. And then we have the KBC void, which is giant, even greater than the giant void, 420/h megaparsecs. So this KBC void is important for us, and that is related with the next item, that we are nowhere in an average position. Because remember, according to the cosmological principle, we say that the universe is homogeneous and isotropic, and our location is not really special, that's what we say. But actually, we are living in a very underdense region. So this is our local neighborhood. We're living in this Virgo cluster. And this is the KBC void that I was talking about. It's an underdense region, and when you compare it to the average distribution in the universe, it's really, really underdense. And there are gravitating structures at every scale, which different geometries apply. We have galaxies, galaxy clusters, we have superclusters, and then we have all those filaments, voids, and walls in which gravity or the geometry is actually different. You cannot assign just one geometry in every scale you look. And the other discussion people give when they talk about inhomogeneous cosmologies, and which is really important, is that general relativity is tested only in the solar system scale, or like isolated objects like black holes. And standard cosmology assumes GR in all scales, because we say that universe is homogeneous, is isotropic in all scales. We set one metric no matter which scale you're trying to measure. And of course, there's no direct proof that GR has to be the final theory, because in physics, we are usually dealing with effective theories anyway, and maybe GR is not the final theory to understand the universe at all scales. Okay, there are some relevant concepts regarding inhomogeneous cosmologies, and those are averaging, back reaction, and fitting. So averaging is about coarse graining, how you smooth out the small scale effects so that you define your large scale structure of the universe in a proper manner. Back reaction is about how the local inhomogeneities, the stuff going in your local neighborhood, let's say, may affect the cosmological dynamics. And the fitting, how you fit your data that you make the observation in your local neighborhood to an average geometry or an average distribution, because you smooth out stuff, right? So the issue is about the non-commutativity during the smoothing out procedure. Let's say you have a metric gravitational field at the solar system scale, and you increase your scale. You smooth out, and then you go to a galaxy scale, and then you smooth out your metric to define the cluster scale or larger scale structures, and then you reach your cosmological scale by doing some coarse graining of your gravitational field. And of course you can do the same for your Einstein tensor. This is the left-hand side of the Einstein equations that includes the curvature terms. You can do this in every smoothing scale, right? But the thing is, Einstein field equations are coupled nonlinear dynamical partial differential equations. That means if you construct an Einstein tensor from an average metric, it's not going to be equal to the average of the Einstein tensor that you built through your original metric. And that is purely because of the nonlinearity of the Einstein equations. That means when you average your Einstein equation, you will not get this term to be equal to be zero, the left-hand side and the right-hand side. So let's say Einstein field equations apply on the solar system scale. You know the metric, you know the gravitational field, and you put your Einstein equations. Once you do the averaging or smoothing out or coarse graining, let's say, you will end up with an additional term that acts like an effective stress energy tensor. And this will happen in every scale. And you smooth out, you get the cluster scale, and go on and reach the cosmological scale. So this is the back reaction effect of the small scale in homogeneities to the global universe. That is what you expect. So that means if we know that the Einstein field equations GR applies on the solar system scale, we should assume that the Einstein field equations hold on an average geometry. And that's what the standard model does, because originally you would expect an additional term here, which the standard model doesn't have, right? It's an assumption that those terms are going to zero in every scale you observe. So in homogeneous cosmology is mostly after this additional term that is showing up when you do the averaging, smoothing out. And then there's the fitting and observations, all those problems with the actual data, how to best fit the local measurements to an average geometry. And how are you going to smooth out your space-time metric or your spatial sections? Smooth out the scalars relevant for the observations, or do you even define those scalars for space-time or for the spatial regions? Are you gonna do some metric averaging via some kinetic theory maybe? And what you get the data, when you get the data actually propagates, the information propagates along your light cone. So should you be doing some light cone averaging rather than, doing the smoothing out on the spatial sections? So those are the questions still under debate in the inhomogeneous cosmology community. So I'll briefly talk about the averaging techniques now. The most famous one that we have is the Buchert spatial averaging. That is the spatial averaging of scalars of your domain. And then there's a covariant approach of Zaloretuno. That is the space-time averaging. So your volume is the domain defined on the space-time itself. And then there's the null cone averaging introduced by Gasparini's team, and that was around 2011. So I'll start with Bucher's averaging. So it averages scalars on spatial domains, and it's not covariant. It depends on how you define your spatial sections. Because in general relativity, there's no one way of foliating space-time into regions of space and time. So there are actually infinitely many ways of doing that. So this kind of averaging depends on how you define your spatial slices. And this is an effective picture with no background. Because remember, in the perturbation theory of the standard model, you have a fixed background, a fixed geometry that you define your perturbations on. But here, there's no background that you specify. That means this back reaction term could react back to redefine your background. In every scale, you define your averaging. So this is how you define the average. The term on the denominator is the three-dimensional volume element, and you basically weigh it in your volume, spatial volume, any scalar. So if you recall the FLRW metric, which has like Euclidean, for the flat case of course, Euclidean space regions that are expanding in every direction homogeneously and isotropically, and this is how you define volume. So here, in this case, since you have some special domain, you can define an effective scale factor for your domain via the volume element you have. You simply take its 1/3 factor, and you define an effective Hubble's parameter. And the other important thing is that this spatial averaging and time evolution do not commute. So let's say initially you have some perturbed initial metric. It's different when you take the average first and then look at its evolution than when you first take the evolution of this metric and then take the averaging. So evolution operator, time evolution operator, and the spatial averaging operator do not commute. And here is its commutation rule. Here theta is the expansion scalar of your fluid elements. So here the Raychaudhuri's equation is relevant. That gives you the change in your expansion scalar. Let's say you have a congruence of matter particles, you have a bunch of word lines. If you want to see how the expansion of this congruence changes, you get the Raychaudhuri, contracted Raychaudhuri equation. Theta is the expansion scalar, as I said. Sigma is the shear. Omega is the vorticity, and you have the term coming from the curvature. And when you consider a Hamiltonian constraint, which is basically the time-time component of your Einstein field equations, with this Raychaudhuri equation, and average them, you get such kind of equations. So I don't know if you remember the Einstein field equations of the FLRW metric that we talked about yesterday. If you turn off these Q terms here, you basically get a similar equation for the homogeneous and isotropic distribution. So those additional terms, term Q, is called the back reaction. And it's given by the variance of the expansion and the shear. So if you go and look at the equation, you see that it's doing the same job as lambda. So you can turn off lambda and turn on back reaction, which is coming from this non-local effect coming from the averaging procedure, and you can create the same effect with the lambda without introducing any new modified way of gravity, etc. So that was an important claim, because if this back reaction term, which is popping up due to this averaging procedure, is positive, it has a repulsive effect, and it can work as dark energy. And if it's negative, it has an attractive effect. And you can even model the behavior of dark matter this time, because dark matter is like acting is like an extra matter that try to clump things into, rather than dark energy has a repulsive effect. So the question of with these kind of construction is whether the effective quantities you get via this averaging procedure is the ones you directly observe. This is a bit tricky in different situations. So this is the question. This should be the question on your mind if you go into the field. The other, okay, I should talk about this coincidence as an aside. So people see this as a coincidence that dark energy starts dominating once structure starts to form. And these kind of averaging techniques gives an explanation for that, because it is the small scale inhomogeneities actually creates this effective behavior, right? So this is a graph from Baudry-Kima, I think Ostrowski and Buchert. He's working in Torun actually. So the vertical line is the omega parameter for the cosmological constant. Remember, it's the dimensionless parameter that gives you the ratio for the energy density divided by the critical density, and the realization factor. So, and the horizontal line is the redshift. You see that the line here, the blue line, is the omega of the cosmological constant, and the dots or the crosses gives you the realization factor for different simulations. You see that there's a correlation between the dominance of the dark energy and the realization of structures. So it was one of the claims that it was the realization of structures at the late times that led to this apparent accelerated expansion phenomena. So it comes from the back reaction, that's the claim. Okay, this is another approach given by Zololetdinov. The analogy he used to introduce this to general relativity is that macroscopic electromagnetic theory can be derived from the microscopic Lorentz-Maxwell theory. And this is a covariant approach for averaging, unlike the spatial averaging that I was talking about. There's no smoothing out of the metric here. And this is how you average your tensor in general. So it doesn't have to be a scalar. You can apply it to any tensor actually. So normally we define tensors at a point. But if you're going to do an averaging of a domain, you need to be able to have a formalism of non-locality, right? So that's when the bi-tensors comes into play. You define tensors at 2 points, and that is a technicality, I would say. And you use propagation objects to how to propagate those tensors from one point to another. And again, this volume element is the one of the overall space-time. So here, this back reaction term that I was talking about that acts effectively, that gives this effective accelerated expansion effect, shows up as a correlation tensor and in the spatial curvature term. And when you take a certain limit, it actually gives the results of the Buchert formalism. But the caveat is that this parallel propagator should satisfy certain conditions and differential equations. And it's tricky to really put your finger on how this affects the magnitude of the back reaction term. Okay, the other approach is the light cone averaging of the Gasparini's team. So here they introduce a window function. Let's say you have the generic space-time. By introducing a window function, you can select in which domain you will do the averaging. So here you can have a truncated light cone. You look back time of your, and this is the most relevant one for the observations, I would say. You can do the averaging on these causally connected spheres, which is embedded on your light cone, or you have this two sphere embedded in the light cone, and you can do the averaging like with a clever window function you choose. So again, there's a non-commutativity of the evolution operator and the averaging procedure, and that gives you the back reaction term that I was talking about. And here, the back reaction shows up as a difference between the average of the redshift drift and the drift of the average redshifts that you observe on your past light cone. So then again, you can have an effective term that gives you this accelerated expansion phenomena. Okay, and then you should maybe go and check what happens in the standard model, right? Standard model is flat. You have the lambda CDM contributions, and you have Gaussian scalar perturbations on a fixed background, homogeneous and isotropic background. And if you want to do some averaging in the standard model, you need this scalar factor in your model, right? That is both affected by the averaging procedure, but you also need it to define the averaging procedure. So it's tricky because the fact that you are fixing your background, you're not allowing your back reaction terms to change your background, gives you a wall to hit, really. So assume that you have this perturbed geometry, FLRW being the background, and you have small perturbations. That's what people assume, even for today. That was true in the early universe, yes, but as I showed you the pictures, that might not be the case for today. But let's say it is small, even today. The affine connection is obtained by taking the partial derivative of this perturbation. And the field equations are going up to second order derivatives of this perturbed metric, right? So that means even if your perturbations are small, their second derivatives are not necessarily small. So those not small terms can show up in the field equations, actually. Okay. Let's assume a perturbed FLRW in the Poisson gauge, and let's go up to second order this time. There was a question about it, I think, yesterday. So this going up to second order will give you a consistency check here. So the effect of back reaction depends on the gauge choice. This is important. It depends on how you define your background and how you define the perturbations on your background. And back reaction terms are related to this contraction of the partial derivatives of the perturbations you introduce to your system. And if you want to find the effect on the sky average Hubble's parameter, what you do is you assume a spectrum for these perturbations, Gaussian maybe, and evaluate the statistics of the sky average Hubble parameter, and then calculate the expectation value, right, to have a fixed value for the Hubble's parameter. And keep in mind that the ensemble average for this perturbation is 0. So that means when you do the sky average, this is the sky average Hubble's parameter, this is the one of the background FLRW, homogeneous isotropic distribution. So the first order terms will give you the variance, and it's the back reaction is actually obtained from the second order terms. And the magnitude of the second order terms are still under debate in the field, because as I said, it's gauge dependent. It depends on the assumptions you put on the model, whether your perturbations are small, whether you want your first derivative of your perturbation to be small, second derivative. So you can put your controls on that. You can define different gauges, and the magnitude of the back reaction is still under debate, I must say. For example, I'll show you a recent debate. There was this Green and Wold paper, which was really famous. So they asked, how well is our universe described by an FLRW model? And the first sentence they have in the abstract is extremely well. So they have this method to smooth out the metrics in every scale, a mathematical method. And they end up with the solution, and they assume small perturbations in their model. And they end up with with a result that the back reaction terms are not relevant for our universe. And that created an outcry in the inhomogeneous cosmology. So they wrote a rebuttal paper with 11 authors. Most are really famous in their field, and actually 2 of them from Torun. And they asked, is there proof that back reaction of inhomogeneities is relevant in cosmology? Because that was the claim of Green and Wold, right? They were saying it's irrelevant. And the first sentence they have in the abstract is no. So it was a critical rebuttal, fight to show that their method was not working. It's not actually, wouldn't work for the real universe, that the method they used is not really relevant to take the averages for our current universe. With the way we define fluid particles is different, and that's not applicable. So yeah. So to sum up, I think I'll sum up now. Standard cosmology is set to fit the observations perfectly. It has certain cosmological parameters. You put it in you match them to the observations, and it fits perfectly. But in exchange for introducing new parameters to the model, like dark matter, dark energy, and actually 95% of the energy budget of the universe is unknown, and they are in this they exist in these new parameters of the model. And in general, dark energy, dark matter, and inflation problems are tend to solve by simply introducing scalar fields to your model. And the physical mechanisms behind the introduction of these scalar fields are actually unknown. So the theoretical community is usually, in general, let's say, is unaware of how the observations are done or how the universe really looks like. And the observational community is unaware of the foundational problems in cosmology. They don't even know that we have those foundational problems in general relativity or in these standard models. Even simple logical problems, I would say. And in order to solve the foundational problems in cosmology, you need to have the full knowledge of the quantum gravity, cosmology, relativity, particle physics, etc. And on top of that, you need to have knowledge of the statistical methods used in the observations nowadays. So the problems are getting so bigger, the observations are becoming so hard to really understand, put your finger on. You need the full knowledge, like hands-on approach, to solve the foundational problems. And I would say that only small fraction of researchers today are attacking the big problems. So we tend to have, 5 papers in a year, and the problems are already hard. And if you do that, if you approach those problems with that state of mind, I'm not sure whether you would get there. But I'm hopeful, because we're at the precision era for cosmology. We have amazing observations. And there are still genuine people who want to solve these problems by putting really huge amount of effort and the risk of, destroying their lives. So I think that is it. Thank you for listening.